Hey everyone, welcome back to Real Analysis 1. This will be part C of Lecture 2. We had just finished previously in part B going with a series of examples where we broke down what the least upper bound property meant in a couple of different contexts. We want to continue on with that. We're going to prove some theorems in a moment that will use a least upper bound property, and these are theorems that we would not have been able to prove without assuming the least upper bound property. But before we do that, we do have a little bit of shopkeeping to do on a couple of related concepts, very related. So let's go ahead and start with what the least upper bound property represents in the case of unbounded sets and of empty sets. Okay, so we'll start with the idea of an unbounded set. So if E is a non-empty subset of R, we set the supremum of E equal to infinity, and that's in the case if E is not bounded above. And we set the the infimum of E equal to negative infinity if E is not bounded below. That should be intuitive. I mean, if a set has no upper bound, then we can say that we simply define the least upper bound to be positive infinity. And if a set is not bounded below, we do likewise set the infimum equal to negative infinity. And I think that's intuitive. What if E is the empty set? If E is the empty set, well, here's the thinking on this, and this could be a little bit confusing for some folks, but if E is the empty set, then every x in R, think about this, then every x in R is an upper bound. Right? So if E is empty, then every x in R is an upper bound, and every x in R is a lower bound. Okay? So if every x in R is an upper bound and every x in R is a lower bound, we would say we set the supremum of the empty set equal to, so what do we think the least upper bound of the empty set ought to be if every x in R is an upper bound? Well, paradoxically enough, it's negative infinity. The least upper bound of the empty set is negative infinity, and the greatest lower bound, the infimum of the empty set, happens to be infinity. Right? So it's kind of the reverse of what you would typically think, but again, keep in mind, this is the empty set, right? So in the empty set, there are no elements, so every element is an upper bound, and every element is also a lower bound. So I think those make sense. This second one is one that sometimes gives people some trouble, but I think if you think it through, the definition makes sense. Okay. Next, we want to talk through the concept of an interval. I mean, intervals are going to play a very important role in pretty much everything we do. So we just want to make sure that we have the idea of an interval clearly clear in our heads. Okay, so let's go ahead and define interval. So for a and b real numbers, with a less than or equal to b, the open interval AB is defined as, we would say a comma b is equal to the set of all x in R, such that x is between a and b, naturally. Right, now the we're kind of falling back on some of the notational things that we've used up until now, probably in mathematics, the idea of less than symbols and versus less than or equal to less than or equal symbols, right? The closed interval, so this would be an open interval, meaning a is strictly less than x, and which is strictly less than b. The closed interval is defined as, right, and so again, kind of bringing all the notation together here. This is all of the x's in R such that a is less than or equal to x and x is less than or equal to b. Right, so all the values between a and b, and also including the endpoints a and b. Okay, and so we have all of, in addition to these, which we're familiar with, there's also the half-open intervals and the infinite intervals. So I won't write all of these down. I'll just give you a sense for it, and I think you can fill in the gaps. The half-open intervals are going to be things like this. Here we're talking about all of the x in the real numbers such that a is less than or equal to x, which is strictly less than b, right? So the half open interval, and you would have one similarly for this. It's not exactly the same, right? But you can see the pattern. And then the infinite intervals. Right? What are the infinite intervals? Well, they're the intervals where you have endpoints that are infinite, right? So for example, a comma infinity. This is all of the real numbers x such that a is less than x, which is less than infinity, right? And there's going to be 4 variations here. You've got a comma infinity, and obviously you've got negative infinity comma a. And then you've also got a comma infinity where the lower endpoint can include a. And then you've got negative infinity comma a where the upper endpoint can include a. Right, so these are kind of half open infinite. Right, so these are open intervals with infinity, and these are half open intervals with infinity. Now notice that what we don't ever have is a closed interval, a closed infinite interval. We never see things like this. All right, so that is your intervals, your infinite intervals cannot include infinity as a value, as an endpoint, right? That doesn't make logical sense, right? So just keep that in mind, right? And so I'm sure most of this stuff will be things you have seen, but we just have to make sure that when we're talking about intervals, we know what we mean. So now, of course, when b is equal to a, the interval can be, you have two options, right? You can have a comma a open, which of course is the empty set. You can also have a comma a closed, which would be just the singleton a, naturally. Okay, and what happens with the half opens? Well, I'm going to leave that to you to think about. What is this all about? I'm going to leave that one to you. Okay, and so these are the intervals. Questions about intervals, right? These are just basically a review of the notation that we're kind of used to. Okay, very good. Let's take another look at another definition here. A subset J of R. A subset J of R is an interval. There's different ways to describe it. Here's another one. A subset J of R is an interval if whenever x and y are in J, right, with x less than y, then every t satisfying x less than t less than y is also in J. Right? So that's intuitive, I hope. Right? If you've got x and y in J and x is less than y, then anything between x and y will have to be in J as well, if we're talking about an interval. Now, intuitively, we know what an interval is, right? It's really just, you think about the real number line. Down here, you've got negative infinity. Up here, you've got positive infinity. You know, and if you've got an a and a b, then an interval is really just everything between them. Okay, and it's all about, you know, do you include the endpoint? Do you not include the endpoint? Right? These are all things that we definitely should be familiar with. We just have to make sure that this is all clear, because we're going to be talking about intervals very rapidly and with a lot of frequency, and we just have to make sure that we know precisely what is meant by it. Okay, so let's go ahead and next take a look at a few consequences of the least upper bound property. Okay, so let's take a look at a few consequences of the least upper bound property. Now, the things that we're going to look at are you know, they're properties of the real numbers that are usually taken for granted. Right? So these things are usually taken for granted. You usually don't even think that you should question these things. That's what it means for something to be taken for granted. But given that we now understand the least upper bound property, we're kind of in a position now to see that they're actually consequences of the least upper bound property. They only work because of the least upper bound property. Okay, so let's take a look at a few of these. So the first one we'll look at, and there's lots and lots of these, and we're just going to pick a few of them. The first one we're going to talk about is known as the Archimedean property. The Archimedean property. Okay, and what does the Archimedean property say? It says that if x and y are real numbers and x is greater than 0, then there exists a natural number such that n times x is greater than y. Okay, you may be saying to yourself, if this is really named after Archimedes, I've not heard of this Archimedean property. Well, it's something that you kind of take for granted. Let's do an example. It's a deceptively simple concept. So let's let x equal 10 and y equal 50. So the Archimedean property says that there's going to exist an n such that n times x is greater than y, which is the same in this case as saying n times 10 is greater than 50. Well, of course, I can come up with such an n easily. I could just say n equals 6. Right, that would work. That's the Archimedean property. Let's see another example. What about x equals 10 and y equals negative 50? And there exists an n such that nx is greater than y. And so that's going to imply that n times 10 is greater than negative 50. Well, that's kind of easy, right? I can easily just say, I can set n equals 1. Right, so 1 times 10 is 10, which is definitely greater than negative 50. So you get the idea. So let's go ahead and prove this. Let's go ahead and prove this. Now, if y is less than or equal to 0, clearly the result is obvious, as in this example. So if y is less than or equal to 0, the result is obvious. Okay. So let's assume, therefore, that y is greater than 0. Okay. We'll use an argument by contradiction. Okay, an argument by contradiction. Okay, so let's start by describing the set A. Let A equal the set of all n times x such that n is in a natural number. Okay. Now, if the result is false, then what? Well, if the result is false, then there does not exist an n natural number. Right? So if the result is false, then there does not exist a natural number n such that n times x is greater than y. Okay? Then n times x would have to be less than or equal to y. And therefore, what? Y would be an upper bound for A. Okay? All right, so this is a very clever little proof. Right? So if the result is false, then there does not exist an n in n natural number such that nx is greater than y, and instead nx would have to be less than or equal to y. And therefore y would be an upper bound for this set A that we've just created. Okay. Now, because A is non-empty, A must have a least upper bound in R. Right, that's the least upper bound property coming in. Okay. So because A is non-empty, A must have a least upper bound in R. So let's go ahead and let alpha equal the supremum of A. Right, and so just to keep in mind what we're talking about, alpha is the supremum of this set, nx such that n is a natural number. Okay. All right, flip pages here. Okay, so alpha is equal to the supremum of A, which is the supremum of this set, nx such that n is a natural number. Okay. Now for some fixed x, right? Okay. Then since x is greater than 0, right, by assumption, right, that's part of the theorem. Since x is greater than 0, alpha minus x must be less than alpha, right? So you're taking alpha, you're subtracting off a positive quantity, that means it's less than alpha. And so therefore, alpha minus x is not an upper bound on A, right? Remember, alpha is the supremum of A, right? So if alpha minus x is less than alpha, it can't be an upper bound. So alpha minus x is not an upper bound on A. And so if alpha minus x is not an upper bound on A, then there exists an mx in A such that alpha minus x is less than mx, right? But then, notice, alpha minus x less than mx implies that alpha is less than mx plus x, right? Right? And so that implies that alpha is less than m plus 1 times x. right? And here we have a problem. We have a contradiction, right? It's a contradiction because m plus 1 times x is certainly an element of A, right? And what we can see here is that alpha equal to the supremum of A is less than an element of A, which of course can't happen. Okay, so then, I mean, we'd have the idea here with this proof by contradiction is then you then go back to the assumption that caused the problem and you flip it. So then there must exist an n in the natural numbers such that nx is greater than y, right? Which proves the result. Okay, so there we go. All right, so that's the idea. That's a great proof, right? So what a clever use of the least upper bound property to prove a theorem that's kind of subtle, right? Certainly easy to understand theorem, but a subtle proof based almost entirely on the concept of the least upper bound property of the real numbers. Right, so this theorem in particular will be useful later when we start to rigorously look at limits. This will be useful later when we look at rigorous limit proofs. Right, we'll talk about sequences and series and such and all kinds of stuff. And this will be something that we'll frequently use. What we'll do is we'll often call on the existence of some positive integer. So we'll call on the existence of some n, right? Some n in the natural numbers, such that, you know, it'll come up in a variety of ways, but we might say things like n epsilon is greater than 1, for example, which is just the Archimedean property. Epsilon's a real number, 1 is a real number, n times epsilon is greater than 1, right? So epsilon will be some positive value, right? So this will fit the, right? So here's like your nx greater than y, right? And we'll use this to do clever things like 1 over n is less than epsilon for all n greater than or equal to capital N, right? And so we'll see this kind of thing later. So it isn't just a, you know, a curiosity that we, you know, chose this theorem. It's also something that will be important, you know, later on as we start to prove more complex things. Okay. The second theorem that I want to pull out here is the following. Right, what this one says is that if x and y are real numbers and x is less than y, then there exists an r rational number, an r in Q, such that x is less than r, which is less than y. Okay. So this is basically saying what? This is basically saying that if you give me any two real numbers, I can always find a rational number between them, right? And so this property is often thought of as the rational numbers being dense in R property, right? So this is often termed as the rationals are, and here's the word that is frequently used, dense in the reals. Right, so the rationals are dense in the reals, meaning no matter how close together x and y happen to be, there's always a rational number between them. That's kind of an interesting thought. If you, I mean, we've obviously seen already that the real numbers exceed the rational numbers in terms of quantity. Well, at least intuitively, we might say as much. But this theorem would suggest that between every two real numbers, there's always a rational number, which kind of makes that whole idea of there are more reals than rationals seem a little bit question. You might call that into it might be called into question here with this term, with this idea. So let's prove this theorem. This is a beautiful theorem, I think. I like it just brings to mind a lot of different and conflicting ideas all into one. And so let's go ahead and prove it. All right, so let's assume that x is greater than or equal to 0. Then, so since y minus x is greater than 0, there's going to exist a natural number such that n times y minus x is greater than 1. Okay, so this is just the Archimedean property. Right? Y minus x is greater than 0, right? So there's, one of the qualifications was that this value here has to be greater than 0, and it is in this case. And so there's going to exist some natural number n such that this times this is greater than 1. Okay? All right, and let's just see what happens here. So n times y minus x greater than 1 implies that n times y minus n times x is greater than 1. Right, and that's going to imply that n times y is greater than 1 plus n times x. That's just some algebra. Okay, just algebra. Okay. Now also, and this one by the previous theorem, k, the set, k and n, the set of natural numbers, such that k is greater than nx, is non-empty. Right, so I can always find, this is going to follow directly from the previous theorem, right? That makes sense, right? Hopefully. Then by the well-ordering principle, there exists a natural number m such that m minus 1 is less than or equal to nx, which is less than or equal to m. Okay, so whatever nx happens to be, I can always find a natural number larger than it, and if I just move over one to the closest natural number, then that natural number and the natural number that precedes it are obviously going to straddle nx. Right? It could be that nx is a natural number, so we have to have less than or equal to, right, as part of the inequality here. Right? So this is going to be true. Right? So far we've got this piece here, which is straightforward. This is an application of the Archimedean property, and this is just algebra. Now this piece here is hopefully very easy to, hopefully you can convince yourself of this very easily, right? This is the well-ordering principle. There exists m and n such that for whatever number, I can always find a natural number on either side of it. Okay. All right. So then, what do we have here? Well, what we have is that nx would be less than m, which would be less than or equal to 1 plus nx, so same idea as this, which will have to naturally be less than ny by this up here. Okay. Right? And so we have this nice inequality here. Right? And we could clean this up. We can just divide n out of all of this. Right? So dividing out n. What happens if we divide out n? Well, then we get x is less than m over n, sorry, which is less than y, right? So we really don't care about this part except insofar as like creating the link. What's really important is this, this, and this. Right, and so there you are, right? So I've got an x and I've got a y. You gave those to me. Those values are from you. And I have just I have constructed a rational number m over n, right? Remember, m and n, m is a natural number, n is also a natural number. Okay, right? And so this is just one case. This is, of course, the case where x is greater than or equal to 0. So there are other cases to consider as well. The other cases are actually somewhat easier, and I'll leave them up to you. Okay, so you can go prove those. Right. So again, this is frequently this theorem here is frequently referred to as the rationals are dense in the reals. Right, and so again, it kind of underscores this subtle relationship between the real numbers and the rational numbers. They're both obviously infinite sets. There are things that are real numbers that aren't rational numbers, but yet every rational number is a real number. And so that sort of implies that there are somehow more real numbers. But this theorem illustrates that between any two real numbers, no matter which two, how close they happen to be, there's always a rational number, right? So all of these ideas are kind of jumbled up in this theorem, and a lot of the content of the coming lectures will be trying to unjumble the relationship of the reals and the rationals. In fact, the next lecture will be a lecture on countable and uncountable sets, and so we'll get into that in detail in the next lecture. Okay. All right, and so one last idea, and then I think we can hang it up for this section. All right, so the final theorem, we won't actually prove this one, but we'll state and prove a corollary of this. The last theorem says that for all real numbers x, for all x in R, where x is greater than 0, and for all natural numbers, all n and n, there exists a unique y in the positive real numbers. Okay, there exists a I think I might have botched that. There exists a unique positive real number such that y raised to the nth power is equal to x. Okay. Right. So this is another one of those qualities of the real numbers we take for granted, but this is basically saying that for any x in R, there's going to be some y that I can raise to some power to equal that x. Right. And furthermore, that y is unique. Right, so for all real numbers x, where x is greater than 0, and for all natural numbers in n, there's going to exist a unique y, positive number, such that y raised to the nth power is equal to x. Okay, so this proof is similar to those that we've seen, but we have to get the square root, the nth roots of real numbers. Okay, so we're not going to prove this one. Let's prove a corollary, though. Let's talk about a corollary. So if a and b are positive real numbers, and if n is a natural number, then AB to the 1 over n power is equal to a to the 1 over n power times b to the 1 over n power. Okay, now this is an easy one to prove, so let's do it quick. Let's let alpha equal 1 over n, or sorry, alpha equal, sorry about that, alpha is equal to a to the 1 over n power, and beta is equal to b to the 1 over n power. Okay, then it's a one-liner, isn't it? AB is equal to alpha to the n, beta to the n, which is equal to alpha beta to the n. Okay, and so that implies that alpha beta is equal to AB to the 1 over n. Okay, so there you go. Simple thing. We'll use this stuff all the time, so we just need to kind of call out some of these concepts and prove them here and there. We're not going to be able to prove everything we come across, but I mean, this is a proof-based course, so we will be proving most things that are stated as theorems we should prove, but not everything. Okay, perfect. So I think that's where we'll leave it. Again, that was a very long lecture, 3-parter, 2.5 hours, but obviously very important, right? So the least upper bound property. Right, least upper bound property, characteristic of R, and in particular not Q. Okay, and so we'll be exploring this obviously in a lot more detail. This property it'll come into play like all the time, daily. So next class will be countable and uncountable sets. And so this is an extremely interesting concept. I think of all of the lectures I ever attended as an undergraduate, this was definitely one of the most interesting in my opinion. Countable and uncountable sets. I will try to do it justice, I really will. But it's one of those things that's kind of mind-blowing, I think, when you first hear it. So, all right, I think we'll leave it at that, and we'll talk to you all next time. Take care.